for today is lasers, but we are specifically going to concentrate on two types of lasers, which are the helium neon laser and the ruby laser. So before we start, let's just do a quick recap of what is laser. Basically, laser is an acronym where L stands for light, A stands for amplification, off, S stands for stimulated, E stands for emission, or R stands for radiation. So that's the full form of laser. It has got certain specific properties because of which it has got enormous application in daily life, and we can just look into some of the properties. So if I just give you a brief of the properties of laser, we can just look into some properties, which are: number one, it is highly unidirectional. That means all the photons that will usually be coming out of a laser system will be only in one particular direction, right? So it is unidirectional, very important property. Secondly, it is monochromatic in nature. So by monochromatic, it means that there will be only a single wavelength that is coming out of the laser. For example, if you consider something like a helium neon laser, the wavelength that it will have basically is 632.8 nanometer, and if you're considering something like a ruby laser, the wavelength output will be in the range of 694 nanometer. Third property which is there, we basically say it's the coherence. So the third property which we need to discuss is coherence. And by coherence, I mean that if you are basically having, let's say, a wave, something like this, and you have another wave, and both of their peaks are matching one below the other, that means that they are in perfect phase. Okay, so this is basically, these two waves has got something which we call as zero phase difference. So this is zero phase difference. And when we also have, let's say, another wave, let's say it starts from here and then it goes on, so that means the phase difference here between these two would be nothing but pi by 2. So this is having a constant phase difference of pi by 2, so we will call it as having a constant phase difference. And of course, the fourth property is it's highly intense. The intensity is very high for a laser action. That is actually one of the reasons that lasers can also be used for mechanical purpose like laser cutting. So you can consider an example of carbon dioxide laser, which is actually a very high intense laser action. Now we can just look into what are the applications of lasers, but then before we go into that applications, you can easily understand the application from some of these properties. See, if you need a monochromatic source of light, you can use a laser action, right? You need for laser cutting and all, for scientific application, for lab experiment, these are some of the major applications of laser action. Apart from that, some important points about lasers are, let's just write down some important points. So a laser, has got certain requirements which are very important. And what are the requirements for a laser action? If we say, there are two main points that we should know. Number one, there should be a presence of a metastable state. Metastable state. And then we should have a process which should be there, which is called population inversion. Population inversion. Now, as we know, basically it's a quantum mechanical concept from quantum mechanics, that when we are talking about an atom, these are actually distributed and energy levels, and somehow if we have more number of atoms in the excited state compared to the ground state, we can say that we have achieved population inversion. Now we can excite the atoms in different ways. We can have an atom excited into the upper energy level, Okay, let's say this is E2 and this is E1, and we know that the energy of the upper energy state will always be greater than E1. We can excite the atom by using some kind of pumping method, optical pumping, electrical pumping, chemical pumping, and so on. And if we have more number of atoms in the excited state, we will have less number of atoms in the ground state. This particular state is called population inversion. So you can see in this example that population inversion has been achieved between E2 and E1. But then there is a problem that in most general cases, when we are talking about the energy levels of atoms, there is something which is called lifetime. That means for how long the atom can be there in the excited state, and mostly it is 10 to the power minus 8 second. And in the ground state, the atoms can stay forever, so the lifetime is more or less infinity. Now metastable is such state which may lie between E2 and E1, but the lifetime of such energy level will be greater. It will be around 10 to the power minus 3 second compared to the upper excited state. So that means that the chances of getting a population inversion between energy level E3, let's say, and E1 is far more compared to E2 and E1. What happens with E2 is by the time the atom gets excited to this energy level, there will be a spontaneous emission and the electrons will come down to this energy state. So this comes down, another atom goes up. So that means you can never achieve a situation where you have more atoms in the excited state. But if you are considering this energy state, which is the metastable state, the atom has enough time to go up, and the other atom which was already excited does not come down in that time frame. So we can say we are having a population inversion between the metastable state and the ground state. Now, a very important term in laser action is stimulated emission. Here we should actually note down something which we call as interaction of radiation with matter. Okay, so this is the second point that we should note. This is basically called interaction of radiation with matter. So when radiation interacts with any kind of matter, there can be three possible things that will happen. By radiation we mean that we can talk about something like photons. So if we are talking about photons interacting, let's say we are considering two energy levels. Okay, let's say this is your E1 and E2, and I will tell that there are three processes that actually might happen. Let's just look into each of them processes one by one. The first process that actually might happen is called induced absorption. So I will use the term here, induced absorption. So let's say I'm basically having an atom which is in the ground state in E1. So we have an atom in the ground state which is E1, and I'm allowing a photon to come in, right? And you know that the energy difference between E1 and E2, I can write it down as E2 minus E1 because E2 is in the higher energy state, is equal to h nu. So if this photon which is coming in has got an energy which is equivalent to the energy difference between E2 and E1, the chances are that the atom in the ground state will get excited and go and sit here. This is actually called pumping, and if you are doing it with the help of a photon, which is called optical pumping. So we have it here, and this is called induced absorption. A ray incident photon is there and it induces an absorption. The second process that might happen when radiation interacts with matter is called stimulated, or let's take up spontaneous first. Okay, let's talk about spontaneous emission. This is called a spontaneous emission. Now, what do you mean by spontaneous emission? Let's say somehow I am able to excite an atom into the upper energy level, and it can't stay there forever because I said that the lifetime on the upper energy level may be 10 to the power minus 8 second. Eventually it is going to come down to the ground state, and as it comes down to the ground state, because of the energy difference between the excited state and the ground state, it is going to emit some radiation which will be equivalent to h nu, equal to the energy difference between E2 and E1. So this is happening on its own, and we call it as spontaneous emission. The third situation might be we are basically having an atom in the excited state, and maybe it's in the metastable state, let's say, and maybe the time here is 10 to the power minus 3 second, and we have an photon which is incident, and the energy difference again here is h nu, and there is a kind of interaction between this incoming photon and the atom which is in the excited state, as a result of which there is a triggering and the atom will come down to the ground state because of this. So what we can say is that we have the incoming photon which comes out, and we have a photon which is again coming out because of the energy difference between E2 and E1. So we have got two photons coming out of it. So this is called stimulated emission. Now this happens because we have got interaction between the incoming photon and the atom which is in the excited state. So this is stimulated emission. So based on this idea of stimulated emission, we have got lasers. Now laser has got three main requirements, and if you remember these three requirements, you can write a very good note on helium neon laser or ruby laser or whatever you are actually writing down on lasers, okay, whatever lasers you are explaining. So we can call it as the requisites of laser action, and requisites of laser action is kind of easy to remember. Let's just write this down. So the first requisite for a laser is an active medium. Now by active medium I mean that the laser action is taking place between which atoms. Okay, it may be a solid laser, it may be a liquid or a gas or a dye laser, right? So let me give you some examples of solid laser. So there are four kinds of lasers we can say. The first example is a solid laser, and it all divides itself. It is divided based on the active medium. So for a solid laser we can take the example of ruby laser, which is a solid state laser. Apart from that, there is YAG laser, which is yttrium aluminum garnet, and this is one of the most common lasers, the lasers that are available, the pointers and all, these are all YAG lasers. The second kind of laser is gas laser, and in this the active medium will be the gases. So helium neon is a good example of a gas laser. Apart from that, we can also talk about carbon dioxide. The third one would be liquid laser, or we call it as the dye lasers. Okay, so dye is basically the medium, so we can talk about dye lasers. Okay, so dye lasers are an example of liquid laser. And the fourth kind of laser is a semiconductor laser. So we have got the semiconductor laser. So all of these differentiation is based on the active medium. And the semiconductor laser, we can take an example as like gallium arsenide and so on. Okay, so we have got the active medium, and these are the examples of the active medium that we have. That's the first requisite. And number two, there should be a pumping source. So let me write it down as pumping source, and they can pump the atom from the ground state to the excited state using different methods. So some of the most prominent methods are the electrical method. Electrical method is actually used in helium neon laser. You can also have something like optical pumping. That means you are applying some kind of photons to be incident, and because of which the atom gets excited. And we can talk about the ruby laser as optical pumping. Okay. Apart from that, there are other processes as well. There may be chemical pumping and so on. So these are some examples. So this is about the active medium, the pumping source. And finally, we have got something which is called the resonant cavity. So I'm going to show you some diagrams of the lasers that we are going to discuss, and that will be actually based on the resonant cavity explanation. So if you are going to write down the construction of a laser, you are supposed to explain these three, okay, and you are going to explain the resonant cavity as well. So having understood the basics of laser in short, we can go and understand what is a helium neon laser. So look into this. When you are going to explain the helium neon laser, the first thing would be you have to explain what is the active medium, right? So when we're talking about helium neon laser, the active medium is nothing but helium and neon, and here we have got the ratio of helium is to neon as 10:1, right? So 10 is helium and neon is to 1. Okay, so that's the active medium that we have, and this is a good example of a gas laser. Okay, then we have got the pumping mechanism. Okay, so in helium neon laser, so this would be your point number 1, and number 2 it will be pumping. So the pumping source, or basically we can write it down as write it down as pumping source. Pumping source is more or less you are applying a potential, you are applying a DC power supply. So we can say it's a voltage, or we can say it's an electrical pumping source, right? It's an electrical pumping source. Okay. And the third point that you should explain when you are writing down the construction is the resonating cavity. So when you are writing down any answer on these lasers, the first thing is you should explain what is that laser all about. So you can say that helium neon laser is a gas laser, okay, and where helium and neon are mixed in the ratio 10:1. I can also talk about the pressure. The pressure of helium within this enclosed chamber within the cavity is 1 millibar, and you know the ratio is 10:1, so that means obviously for neon it will be 0.1 millibar. Okay, so this is for helium pressure and this is for neon pressure, right? So you can explain it that way, and then you can say that the active medium is helium and neon, and then we can talk about the pumping source, which is electrical in nature, and finally the resonating cavity. So when we want to explain the resonating cavity, you can explain it very easily and it's not very complicated, you can see. So let's try explaining the resonating cavity now. So let me just extend this picture. So if you look here, you can see that you basically have an enclosed chamber and we have got the helium neon gas within it. Now on one side we have got the output coupler, which is actually a mirror, which is 99% silver. On the other side it is a highly reflecting end because the mirror is 100% silver. So let's say this is your anode and this is your cathode, and when we are applying a very high voltage, let's say around 10 kilovolt, the atoms or the electrons which are there in helium okay, gets excited. Okay, it keeps on moving very fast, and then as a result the neon atom will also get excited because the helium atom will come and strike the neon gas atoms, and this is actually done inside the entire glass tube. So if you want to explain the resonating cavity, this much explanation should be okay. Okay, and then very important part is to explain the working of a laser. So when you want to explain the working of a laser, you are basically going to talk about the energy level diagram. So whenever you're writing down an answer on laser, it's very important that you actually write down or draw the energy level diagram. So first you draw or write down the energy level diagram and then explain it, and then that should be enough for getting good marks for your exam. So let's just talk about the energy level diagram and look into it. The first thing is why there is neon and helium mixed together. So a very important reason is that the energy levels that the helium has is comparable to the energy level of neon. You can see that this energy level, the gap between the ground state and the energy level which is situated here, is similar to the energy level which is there for neon as well. This is very important for something which we call as resonance. Okay, the matching of the energy levels is happening here. Okay, it's important. So let's just have a look on how exactly the working of a laser, helium neon laser is. So what happens is you are applying some electrical energy and the helium atom gets excited. Okay, and excited, maybe it will go to this energy level, it will go to this energy level. Now helium is in the excited state and the neon atoms may be in the ground state. Now if let's take an example. If an object is here and if we have a body which is moving with some speed v, and this is at rest, it comes and hits the body, and then this will actually come to rest, and this particular body will start moving with, let's say, velocity v. So the velocity transfer is there, or energy transfer is there, and we can call it as an elastic collision. Now here, if we actually want to excite the neon atom from this energy level, let's say from this energy level, we want to excite a neon atom from this energy level to this energy level, you need this much of energy, right? Or if you want to excite it to this energy level, you need this much of energy. Very important. So what happens is, if the helium atom is excited, it will have that much of energy, and when it hits the neon atom, it is going to transfer this much amount of energy or this much amount of energy to the neon atom, and this much amount of energy is okay for exciting an atom from this energy level to this energy level, because the energy levels of helium and neon are matching. That is the main reason why we cannot mix any other gas with helium so that we can get a laser action. The energy level should be more or less comparable. So we have the transfer of energy from helium to neon, and the atom gets excited from this energy level to this energy level, or this energy level to this energy level. Now what happens is, there will be spontaneous emission, and it's not that we are just having these two energy levels. There are other energy levels as well. For example, this 4p energy level, 4s energy level, and so on. And if an atom gets de-excited from 5s to 4p, it is also going to emit some radiation. Now, helium neon laser is a low output laser. That means it does not generate too much of heat, because you are going to have this output, and this actually lies in the IR radiation. We're basically having the IR radiation coming out of it, which is not visible, because of which a slight amount of heat is generated. So there is some kind of radiation coming out of it. If we have a transition from 4s to 3p, again we are going to have an IR radiation which is coming out of it. But then if we have a transition from 5s to 3p, we are going to have an output of 632.8 nanometer, which will result in the monochromatic constituent wavelength of a helium neon laser. Now all of these processes happens at the same time, okay, and in the process we are also having this photon which is actually coming out. Now you might ask that we said that laser is stimulated emission, but this is happening spontaneously. Now when this radiation gets emitted and the entire setup is enclosed within this resonating cavity, this radiation of 632 point this radiation of 632.8 nanometer will move to and fro, and when by the time it keeps on moving to and fro, there are more atoms of neon which goes into the excited state here and here, and this radiation will trigger those excited atoms. As a result, all of these atoms are going to come down to the ground state at the same time, or maybe we can say going to come down from 5s to the 3p state at the same time, as a result of which we are going to have so many photons which are coming out at the same time in one particular direction, as a result of which we are going to have the laser action. So this is how our helium neon laser works. When you are actually explaining the laser action, you should concentrate on the energy level diagram, and if you are able to explain the energy level diagram properly, that should be enough for your working principle. So that's very important. So that's how a helium neon laser works. A similar explanation can also be taken up for ruby laser. Let's just have a look into it, a very quick run through. If you look into the ruby laser, okay, let me write down the important points here, which already you can guess. The first thing is what's the active medium. So you can say the first thing about ruby laser, that it's a solid state laser. In fact, it is very interesting. I have not told you about the year. If I just go back to the previous slide, the helium neon laser was actually discovered in the year 1961 in Bell Labs, okay, but ruby laser is actually the first ever laser to be discovered, and it was actually discovered in the year 1960. So that was the first ever laser, solid state laser obviously, but among the lasers also this was the first laser ever discovered. So if you look into the ruby laser, the block diagram of the resonating cavity, we can have a look into this, and this is basically a ruby rod which is there, and this ruby rod is the active medium, we can say. So if we talk about the active medium, it is nothing but ruby, first thing, and we have got one side to be totally polished, which is the full reflecting end, and other side is partially reflecting, through which the lasers are usually coming out, okay, and this is again enclosed in a glass tube. Now we basically have a discharge tube or a Renon discharge tube. So that means we are going to talk about the second point, which is the pumping source or the energy source. Now the pumping source or the energy source in this case is more or less optical in nature, and let me tell you what is the source that we are actually using, and that is actually a flash bulb. It is basically a flash bulb. So if you remember, or if you have seen photography, okay, or maybe you are using your camera, mobile camera even, if you are switching on the fan, switching on the flash, when you are taking up the snap, the flash switches on and then switches off. So the intensity is very high. Normally in functions and the cameramen with the camera that they are using, the flash bulb are very high, having a very high intensity. So that is a good example of flash bulb, and similar bulbs are attached around the ruby laser. So as soon as some power is switched on, the flash bulb will give out the flashes of light, that is, it will give out photon, and that photon is going to excite the atoms in the ruby. So that means this is a good example of optical pumping phenomenon. So that is what is done in the ruby laser. Okay. And finally, the third point that you should discuss is the resonating cavity. So this is your resonating cavity. So when you explain about ruby laser, you should know what is a ruby basically. So you know sapphire, you know Al2O3, Al2O3, and if you are doping it with chromium Cr3 plus, you are going to have ruby. So this is actually nothing but the ruby, and the color of ruby laser is more or less red. You know, it's around 694 nanometer. Helium neon and ruby laser are very, the wavelengths are closer, so they are having different shades of red. So this chromium is actually responsible for the color of the ruby laser. So we have the resonating cavity, and once you have explained the resonating cavity, that means you have finished up with your construction part. Now let's try explaining the energy level diagram. Now if you look into the energy level diagram of a ruby laser, is comparatively simpler compared to the helium neon laser. This is a 3-level laser system, so we have to remember this. This is a 3-level laser system. 3-level laser. So you can see there will be a ground state, there will be an excited state, and there will be a metastable state. So we are going to have a radiation which is coming in, okay, and it may be having a wavelength of 5500 angstrom, and that radiation is given out by the flash bulb, and then the atom gets excited, and then there is a transition from this E3 to E2. E2 is the metastable state as per the diagram, and we are not going to have any kind of radiation coming out of it. Of course, some kind of heat might be generated, but then this is the metastable state. The atom stays here for a longer period, so we have more and more atoms here. Population inversion is achieved, and as the atoms come down with spontaneous emission, we are going to have this radiation. Now this again is going to move in the resonating cavity to and fro, and then eventually when we have more atoms in the excited state, this one radiation can result in triggering the atoms in the excited state E2, that is the metastable state, and we can have so many atoms coming down at the same time, and we have the laser action. Okay, so that is very important in ruby laser. So when you explain the working of a laser, you have to start with first the construction, and in construction you should explain what is the active medium all about, explain it a bit, and then go for the pumping process. In this case it's optical, and we are using a flash bulb for it, and then finally explain the resonating cavity. For construction you can draw the energy level diagram, okay, and then after that when you explain the energy level diagram, you know that the working principle is easily explained. So that's all for laser, and helium neon laser or ruby laser forms a very important part of any syllabus where we are studying lasers.